again, we talk about the following scheme, that is xk plus 1 equals whatever. Okay, so we have this iterative scheme, that is alright. So we have this iterative scheme, that is we plug in xk to find out xk plus 1. So a more precise characterization is, okay, so we plug in xk and the gradient at xk to this capital F. So this capital F is whatever like we design, okay. So we can even make it fancier that we add Hessian to the picture, okay. But whatever this is an iterative scheme, okay. So based on the previous iteration, we find the value of next iteration. Okay. If we have a linear convergence, so an equivalent condition is, and now let's assume that x star is a local minimizer. Okay, so then the rate of convergence is characterized by limit. Okay, by limit, but it can be also characterized by the following inequalities. That is linear convergence. This one is less than or equal to mu xk subtract x star. So this is saying, and for mu from 0 to 1. So this is saying is essentially at every iteration, okay, the error. So this is the error. This is how far away we are from the local minimizer at the current iteration. This is how far away we're from the local minimizer at next iteration. So every time the distance shrinks a little bit, okay. And as we can see, so if this is 1, then we'll have a geometric series that is mu to the k power. So it converges to 0, okay. But it's still not fast enough. So I'm saying why it's not ideal is later on we'll see an example. So even though we haven't proved the convergence of CG, but I wrote the convergence on the board, and so we'll use that as an example to illustrate why linear convergence is not very favorable. So we have a superlinear convergence. To be specific, we have a quadratic convergence. Okay. Quadratic convergence is when the p in our homework 2 in that problem is 2. Okay, so then equivalently we can characterize the convergence as, okay, and keep in mind we have c here, so we have constant c here. So equivalently it can be characterized by this inequality, and this time is for c, not just in 0, 1, but from 0 to plus infinity. So both of these are like for sufficiently large k. So now let's look at the rate of convergence of CG. So CG for quadratic function. Like CG is the state of the art for quadratic programming, quadratic function minimization, whatever we like to call it. And its rate of convergence is okay, and this is in Q norm. All right. So where f of x is 1/2 x transpose qx subtract b transpose x, which is a quadratic function. So it's that. So C1 is some constant that depends on our problem and our initial x. Okay. So C1 C1 is problem dependent. All right. And kappa is our condition number. So kappa is lambda maximum of Q divided by lambda minimum of Q. And for Q, that is symmetric positive definite. Okay, so this was what we learned. So the method we tried to derive in the past few weeks, and the convergence. So I decided to skip the convergence, but it uses Krylov subspace. And so I'll post my notes on Canvas. So why this is not ideal? So let's think about the following example. Okay. For linear convergence, so let's do a thought experiment. All right. Let's assume, okay, at kth iteration, our distance to the local minimizer is 0.1. So 0.1 is like really small. Okay. However, our problem is really yield conditioned in the sense that when it's yield conditioned, it means square root of kappa minus 1 and square root of kappa plus 1, even though this one is very close to 1, okay, right? We can think about 100 subtract 1 divided by 100 plus 1. It's less than 1, but it's very close to 1. So let's say this is approximately 1, all right? But this C1 is really bad. This C1 maybe like 10, okay? So let's say C1, let's say this is 10.1 or something, okay? And kappa let's say, okay? I mean, this is just our thought experiment. Now we run the CG for one iteration, okay? What happens is so based on the multiplication of the three numbers together, all right? Our error doesn't, I mean, estimate for error doesn't decrease much, okay? These two doesn't change. And the error, we run one more iteration, it still doesn't change. So there is no guarantee that this error will shrink if we have a bad problem, okay? So this is a drawback of linear convergence. And when we read the proof of CG, we find, oh, C1 really is problem dependent because it has to like it depends on a polynomial, like a combination of polynomials of all eigenvalues. So it's like because eigenvalues for a square matrix can be anything, right? As long as it's positive definite, it can be any like numbers. And so there is no real guarantee that C1 is a small number, unless we really search like the polynomial space for a long, long time. But my point is linear convergence is not favorable in this part. But if we look at the homework, okay, if we look at the homework, so a typical sequence of the error for linear convergence is mu to the kth power. All right? Mu from 0 to 1. But a typical sequence for quadratic convergence is 2 to the, this doesn't have to be 2. I mean, so but here it's minus 2 to the kth power. All right. This sequence decreases really, really fast. So now think about the same problem here. So if we have quadratic convergence, okay. We run the same iteration. So this is going to be less than 10.1 times 99 divided by 101 times the square of that. All right. So this is approximately right? So it's square. Wait, no. Sorry, we don't have. Don't have this. Okay. So let's assume like our quadratic convergence. So let's assume something like this. So let's assume we have our quadratic convergence like this. And again, we have the same assumption that okay. So let me see how did I choose my numbers. So here I just want to illustrate. Okay, so let's suppose this C2 let's suppose C2 is like 1. Okay. Then what happens is so this one is less than the square of that, and if we run one more iteration, it decreases even furthermore. Okay. So if some method has quadratic convergence, I mean, it's really nice. So now let's look at Newton method. But the idea that we learn Newton method is not really Newton method. So we want to illustrate Newton method is nice, but we won't use this. This is not practical. Okay. So Newton method is as follows. So suppose, so we have, okay. So this is the assumption. So f of x is smooth, and it doesn't have to be quadratic. Okay. So because for quadratic function, Q is SPD, CG is already state of the art. So f of x is in general smooth convex function. So what does convex function mean is, so this is our Hessian matrix. And the Hessian matrix is positive. So for every x. Okay. So this is our assumption for Newton method. Now let's look at the actual Newton method. Okay. So Newton method again it's the same iterative scheme. Okay, we want to find, so our problem is still, we want to find the local minimizer of this function. So for k equals 0, 1, etc., and given the initial guess, the k plus 1's iterate is kth iterate subtract. This is a Hessian matrix evaluated at k, kth iterate. But we have to take the inverse of it. Okay. Gradient of f of evaluated at k iterate. So this is Newton's method. So this is a matrix. Okay, so this is a Hessian matrix.
Is that the step side?
Exactly. So this is like a matrix. Okay, this is a Hessian matrix. So the inverse of the Hessian matrix is like our step size. All right. So the step size is so advanced that this is a, think about this. This is an m by m matrix. This, so negative gradient is our descent direction. So a Hessian matrix is a matrix. So it's like a very complex combination of different descent direction together. And we'll prove, we'll get quadratic convergence for this method, okay, under many assumptions. So this is like a very complicated step size. So why we say Newton method is not feasible and we won't use it, that's why we want to introduce. So in the second half of the semester, we'll learn what is called quasi-Newton. It's our state-of-the-art optimization method right now. For machine learning. So we'll learn basically BFGS, and it's named after 4 guys. Unfortunately, I don't remember the first guy's name. It's Boyden, but so I think it's Boyden, Fletcher. I forgot the and the fourth, but anyway, so let's look at this method. Okay, equivalently. So equivalently, here we're going to illustrate why it's not feasible. Okay, equivalently, it's equivalent to step 1 is we solve a decent direction, that is decay in, so this is our Hessian matrix. Okay, so we denote this as H superscript K. Okay, then is we solve the following linear system, that is H of K dk equals gradient, let's use negative gradient, okay, so we solve this linear system, that is H times our step, let's say the vector we want to step in, equals the negative gradient. Okay. All right. So this is solving a linear system. So this is an m by m matrix. All right. And second step is we basically, once we find the step, we update our xk. Okay. So this is equivalent, as we can see, because we assume this is invertible, right? So this is positive. If it's convex and this is positive, means every of its eigenvalue is positive, so it's invertible. So as long as it doesn't have 0 eigenvalue, this is an invertible matrix. Okay. So now let's look at this. Okay. We have to solve a linear system, and this is very expensive. So this is very expensive. This is as expensive as solving a quadratic So how expensive is Newton's method is each step we have to solve this linear system. And think about our quadratic minimization problem. That is, we minimize this function q being SPD, and it's equivalent of solving m by m matrix times x star equals b. So for Newton's method, every single iteration is as expensive as a quadratic minimization to minimize the whole thing. Okay? So that's why this is expensive. Because every iteration is equivalent, as expensive as maybe 100 iterations as before. Okay? But this is very nice. Let's see the convergence of Newton's method. And it's also a very intuitive proof, because we'll see that where this thing pops up. Okay. So theorem. So Newton method convergence. So let's suppose. So suppose f is a C3 function, which means or the third derivative. So f can be differentiated. Up to third order. With continuous derivatives. So, and the other setting is, of course, okay, so we assume, okay, f has a local minimizer x star, and okay, so and the Hessian at this local minimizer is positive. Okay. So once we have these settings, so if okay, xk is sufficiently close to x star in the sense that there exists an epsilon that is greater than 0, so the norm in consideration, so let's just talk about L2 norm in this case. Okay. So if xk is sufficiently close to our local minimizer, in the sense that the following is true. That means there exists an epsilon that the distance from our current iterate to the local minimizer is less than epsilon. And then we have the quadratic convergence. That is, then our next iterate is less than or equal to c times the previous iterate area squared. Okay, so this is the quadratic convergence. So this is, given our current computing power, the best possible method we can have, or say the best possible, basically human is constrained by this second order minimization, because taking the third order tensor derivative is basically infeasible given the current computing power. Yeah. So let's do a proof. So let's write down Newton's method. So let's just copy paste this guy here and subtract x star on both sides. So this is a way to derive area equations for every iterative scheme. That is, we subtract x star on both sides. Okay, so then we have, this is subtract okay. So then let's denote, this guy as capital H of K, okay. And let's denote this guy as G of K. All right. So what we can do is, because h of k, okay, where has it? So first we want to invert h of k, right? This is invert h of k. We have to show that this exists, okay? So why this exists is because this is sufficiently close to that, okay? So now let's argue. So because this guy is positive, right? So by continuity, so if f has continuous up to third derivative, then so this function C1. Okay. So a more precise notation will be using dot. It means this is our variable. So this is C1 just means, okay, and there exists a neighborhood. So this is literally the definition of continuity. So if we have continuity, if a function at one point is positive, then there exists a small neighborhood around that point that this function on that neighborhood is positive as well. So definition of continuity. So there exists a neighborhood. So x subtract x star that whenever x is less than, x subtract x star is less than epsilon, such that the Hessian at this point is positive as well. So it's a positive. Hessian is already symmetric. So if it's positive, it's a symmetric positive definite matrix. So it's invertible. Okay. So then we have our assumption here. Okay. So xk, then we assume, so xk is sufficiently close. So our assumption guarantees, so assumption is xk is in this neighborhood. All right. So if we have this assumption, this formula is okay. So if xk is sufficiently close to x star, this is okay. And then we can pull out this inverse matrix, okay, on both terms. And the first term doesn't even have this inverse matrix, then we can make up a matrix. Okay. So this is GK. All right. So we want to derive a formula on this term. What we can do is, let's recall our Taylor formula. So everything boils down to calculus, even for the most advanced optimization research. So people still using Taylor expansion because that's the only tool we have. So Taylor expansion at a point. So if we want to expand around f star, that is, so let me directly write down x star here. Then this is gradient at gradient f, evaluate x star, inner product with x subtract x star, and with plus then with plus this x subtract x star Hessian at x star x subtract x star. So an equivalent, equivalent formula we had, what we had was like this is like x star plus b, okay, equals x star, and for many of the time we add this alpha here as our step size, then we have this is alpha gradient f at x star, and this one is the d direction, okay. And then we have two alpha popping out, so we have this alpha square, which is step size. This is transpose, and this is d transpose. Hessian of f star t. Okay. Now what happens is, we want to use this formula. We want to use this formula for gradient of f here. So this is 7. 8. So if we use this, we'll find the gradient, okay, of f. So how to apply this is, we just change f to gradient f, f to gradient f. Then gradient f becomes Hessian of f, and then next one is second order term. So what happens is, we have this is gradient of f of x. So leave a space here where we'll fill in this x superscript k, okay, equals. So we're just copying that formula. All right. But now this becomes the Hessian of f, okay, at x star. Feeling okay. Yeah, I don't want that. Actually, I want a Hessian of xk. Okay. So this will be our x star. Okay. So then this will become x star subtract xk. So this will be our xk iterate, and this will be our Hessian's k iterate. Okay. At xk, sorry. Okay. Yes. And then plus c times xk subtract x star squared. So this one equals big O of x subtract x star transpose x subtract x star. This is by Rayleigh's inequality. Now let's look at this formula. Okay. X star is our local minimizer, so this is 0, and because of the first order necessary condition. Okay. So this is our GK. So this is our H of K. So what happens is, let's move these two terms to the left. Then what happens will be, so H of K. So we subtract this to the left, so we can flip the order of these two. So this is our GK. All right. Now let's just compare the left-hand side with this, with what's inside the parentheses of the error equation. So right there, left-hand side, with what's inside this parentheses right here. So what happens is, inside this parentheses is a constant, okay, times the square of this. Which means we have this is so what does this C depend on? C depend on let me still write down in plain English. Okay. So C depend on what? So here C is the Hessian of gradient of f, which means C depend on f's third derivative. Okay. So f third order derivative. All right. So C can be bounded by, C can be set as, so here I'll use some norm notation, that is F's C3 norm. So this is basically the maximum possible third order derivative for F. Okay, evaluated at every point. So C is bounded by this. And now let's look at this. Okay. All right. So the Hessian H of K, what happens is we assume H of K, so we showed that H of K is positive. Okay. So HK inverse So think about this. Okay, let's use a simple matrix to demonstrate. All right. So if H is this lambda 1, lambda 2, so here when we learn our class, in general, everything is presented in n dimension. Okay. However, we can always fall back to 2 dimension and set the simplest possible problem to check. Okay, so what happens? So this is a common way of doing research. Is we dial ourselves back in a very simple case, but illustrative case. Okay, which is 2 dimensions. So lambda 1, lambda 2 are the eigenvalues of H because this is a diagonal matrix. Okay. So H inverse is lambda 1 inverse, lambda 2 inverse, right? Okay. So what happens is, if we want to get an estimate of a matrix inverse, multiply with something. What happens is, this H of inverse is greater than, it depends on, its invertibility depends on its minimum eigenvalue. So it's okay. Sorry. It's minimum. Okay. So H inverse's eigenvalue is lambda 1 inverse and lambda 2 inverse. So it depends on the minimum eigenvalue of these two. What is this? So this is actually the maximum of the two. Take inverse, right? So now again, we assume F has continuous derivative up to the 3rd order, and which means it has continuous derivative in the 2nd order. So H inverse, actually, this one depends on. So this one depends on FC2. Okay. So because it depends on the maximum eigenvalue of lambda 1, lambda 2, which is original H's eigenvalue, which in turns is the maximum possible 2nd derivative. Okay. So now we're done. So this is less than or equal to a C, C1 when we take the norm. So yeah, let me use a new line. Use a new line. So when we take the norm on both sides, I think I skipped this. So when we take the norm on both sides, so it's less than HK inverse norm, and C K subtract X star norm square. So this one depends on the maximum possible norm of F's 2nd derivative. Depends on C2, and this C depends on the maximum possible of F's 3rd derivative. Okay. So now we're done. We have actually done our proof. Okay. It's quadratic convergence when we have these many assumptions. Okay. xk is sufficiently close to x star, and f has to be third order, differentiable, and blah blah blah, and this has to be sufficiently close to this. Now we have a convergence. So there are so many caveats. It's not, the result is nice, but we have too many assumptions. It renders it impractical in practice. So, and then next class we'll do a review, and then we'll do midterm, and then we'll come back to this. So we'll design a new method that we don't have to solve for the Hessian inverse, but we can still get a very close quadratic convergence, which is called quasi-Newton method. So now let me talk about the homework. Okay. So homework 3, let's talk about first problem. The first problem, all I want to show is problem 1. So problem 1 is assuming where Vi is an eigenvector of Q. Okay. So in this homework, we are all doing this quadratic function x. So f is x transpose Q x divided by 2. Subtract B transpose x. So it asks us, when we use steepest descent, we'll get to the x star in one iteration. This actually tells us to show that x1 is x star. Okay. So essentially this is showing, but so want to show this is our goal. But still, let's write down our gradient descent algorithm. So, because it's a quadratic function, we can write down this explicitly. Sorry, not right. Okay. So let's still write down the problem here. So f is 1/2 x transpose Q x subtract x transpose B, and the gradient of f is Qx subtract B, but in the meantime, this is Q, so this formula is very helpful as well, because we know that Qx star is B. So our local minimizer satisfies Q times the local minimizer is B. So minimizing this is equivalent to solving this linear system. And then we have this now. So now the interesting thing happens. Okay. This is Q x0 subtract x star. Okay. Now we use that our assumption that x0 subtract x star is an eigendirection. Okay. That is, it's Q times beta times Vi. Okay. Beta is a constant. So beta is some real constant. So this equals two constants, okay? And Q VI, all right. What does it mean by eigendirection? Eigendirection means Q times VI is a constant times VI, okay? So now this becomes this is the eigenvalue corresponding to VI. So now we have three constants. So this is a real constant. Now if we look at this formula, what it tells us is, okay, so think about this. So I'll stop here. The rest will be completed by you, okay? But here I'll illustrate one thing. Think about this. So this is our initial guess, okay? So this is our X star. So let me draw a picture. You guys will know why I'm saying this actually already proved the problem. But you need to just add a few words saying so if this is our X initial guess, all right, maybe this is our X star, okay, and we assume X0 subtract X star is a constant times a vector, right? So we assume this vector X star subtract X0 is our eigendirection, okay? So on this line, okay, we do a line search on which line? We do a line search in this direction, okay? So this is our line search direction. And this is like beta VI. And it happens that the gradient of X0 is in this direction, right? This is our gradient at X0, okay? So we do a line search on this line. We find the minimum possible function value on this line, and X star happens to be on this line, okay? So what we want to show is, we want to show X star is in the line that we do the line search. Okay, so if we translate it to mathematical language, it means we want to show that X star is in the following set, that is X0 minus alpha. Let me change it to another letter. Let's change it to gamma because we used alpha there. So basically this is what we want to show. If we do a line search, it means okay, X star can be expressed as this. Then our next iteration will hit X star because we search on a line and X star happens to be on this line. Then what up?
What you have written there for?
For some gamma, that is a real number. So there's a lot of research. So in the top one machine learning conference called ICLEAR, so International Conference on Learning Representation, back in 2019, okay, there was a paper called lottery ticket hypothesis. So it's about this thing. So if you're interested in, I mean, if you have learned probability before, okay, and are very familiar with linear algebra, for example, spectral analysis. So I have a little project about this, how to optimize a neural network. So if you're interested, comment on it. Okay. So now let's look at problem number 2. Okay. Because training neural network is, in a sense, it's looking for like an invariant, certain invariant direction, which is very similar to find eigen direction or whatever. But neural network is a nonlinear thing, so we have to be very careful to characterize that. So it says basically what happens is Q orthogonal set. Okay, so this is what we did in class. So we showed. So this is like a complementary exercise for the class. Okay. So in the class for CG, remember, what we did is we did a subspace search on the subspace generated by this. Okay. We did a subspace search generated by this. And we assume these are, remember, so we assume these are Q orthogonal in the sense that the Q inner product or dI transpose Q dj is 0. Okay. If I is not j, so this is our assumption. Okay. We actually, by this assumption, so we actually assume automatically d0 up to dk form a basis. Okay. But to form a basis, we have to show they are linearly independent in the first place. Okay. So this exercise kind of shows that. So it's so PIPJ is it's Q orthogonal, so this set, how many total? So it's n, okay. So then we want to show this is linearly independent. All right. So then we want to use proof by contradiction, which is we assume, so in turn we assume this set of vectors is linearly dependent. Okay. So if we assume this set of vectors is linearly dependent, we just use the definition of linearly dependency. That is, there exist alpha 1, alpha 2, alpha 3 that are not all zeros. Okay. Such that alpha 1, P1 plus alpha 2, P2, dot, 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 equals 0. Okay.
Can we do vice versa? Like, assume that they are linear independent and find like one of the like coefficients should be like 0. So like they contradict each other.
You assume this is linearly independent or dependent?
First like independent then we find like, that some of like, the coefficients like the alpha should be 0. And
Okay.
because like
So
when you-
if we want to show, so this is, so that's a good point, okay? But the answer is unfortunately wrong. Because if we want to show negation, okay? So I understand many of us hasn't taken a formal mathematical proof class, so like playing with these statements might be difficult, but but that's a very good point, okay? So when we try to use proof by contradiction is for example, so when we have statement A, okay? It's like a positive statement, okay? So for example, it's like for any epsilon, okay? And then there's something like, so something is true for this epsilon, okay? And then what we call is, this is a positive statement, okay? This is a positive statement, all right? Then, if we want to find the contrapositive statement, which means we negate the statement, is then the for any will become exist. So their existence is epsilon, and this thing, this something is false for this epsilon. Okay. So now if we want to directly show linear independency, it becomes for any, we have to show for any alpha 1, alpha 2, till alpha n, and each of them is a real number, okay? For any such that alpha 1, alpha 2 is not 0. This is difficult to show because we have to show all of them. Okay, if we want to show linearly independence, so this is equivalent as this is equivalent definition of linearly independency. Okay, so we have to show for all possible. But if we negate this statement, that's why sometimes proof by contradiction is much easier, because once we negate the statement, the for any becomes exist. So for this proof, we only have to find one possible alpha, and we're done. So that's why sometimes proof by contradiction is a much simpler thing than directly prove linear independence. Okay. So now let's continue. So, which means. So if we have this assumption, all right, so basically it says, oh, the linear combination of these vectors are 0, okay? Now what happens is, we take advantage of, so this is the norm, all right? So basically so this thing is a norm. What does it mean by a norm is, if something's norm is 0, then this thing is 0. Okay? So now we take the Q norm of this guy. Because that guy is 0, Q norm must be 0. Okay? The Q norm is taking the Q inner product. Okay, so it's alpha 1, P1, dot, till alpha n, Pn. All right. So alpha 1 P1 plus alpha n Pn Q, okay, is 0. Good? Now we expand this, okay? So the expansion is the same thing as if we have a sum. Let me use B1, B2 plus up to Bn. We'll take square. It's essentially it's a combinatorial problem. This equals what? This equals summation of bi squared plus 2 times summation I is less than j bi bj. So if we have all possible ij combination, then it is this. I is not j. We remove this too. Okay. So same thing here. So it is summation of alpha I pi alpha I pi q inner product I from 1 to n plus I is less than j 2 times, and ij takes up to n, that alpha I pi alpha j pj. For this, alpha j, alpha I are numbers, so we can pull them out. Okay. The left is pi inner product with pj, but using the q inner product, so that all of these terms are gone. Okay. Because I is less than j just means I is not j. So all these terms are 0. So we're left with these, which is we'll have this is alpha I square pi q naught. Okay. So the q inner product is q norm squared. And then we make use of, then what happens is we make use of the assumption that we assume, because in the very beginning of the problem, it says, consider a set of a non-zero vector. So from linear algebra, we know if a set has 0 vector, then it's 0. Sorry, then it's linearly dependent. Okay. And then the rest is pretty straightforward. Okay. So we have this is 0. We have a bunch of guy, and especially the sum of alpha I, with the square, that is 0. And we want to argue every alpha I is 0. So we want to argue alpha 1 equals alpha 2 equals alpha n is 0, and then we reach the contradiction. We want to use this equality to argue that every alpha I is 0, then it contradicts with this. Okay?
Thank you.
Sorry to go over a little bit. So next class we'll go through the practice method. And also, what's the due date for this homework?
Today.
Today? Yeah, let me make it next Tuesday, okay? Okay?
Thank you.
Yeah.
Thank you.
Also, can you extend the code?